Hello and welcome. Today we're diving into one of the greatest scientific achievements ever, a map that literally organizes the entire universe. We're talking about the periodic table.
So just think about that for a second. If someone handed you a box containing one of every single basic ingredient in the cosmos, where would you even begin? I mean, what a challenge. That's exactly what scientists were up against trying to make sense of the elements. And we're not talking about just a few ingredients. There are over 100 of these things, and each one has its own unique personality. It was a massive puzzle. Scientists knew there had to be some kind of hidden logic, a pattern in all that chaos.
So, what do you do when you're faced with a giant, complicated problem? You simplify it, you break it down, and that's exactly what they did. The first step was to forget about all 100 plus elements and just sort them into two big teams, based on things they could actually see and test.
And wow, the difference was like night and day. On one side, you have team metal, shiny, great at conducting heat and electricity, you can bend them, and they're mostly solid. Then on the other side, you've got team non-metal. They're dull, they're terrible conductors, and they can be solids, liquids, or gases. This simple split was the very first step toward finding some order. But, just having two big piles, that's a start, but it's not the whole story. Not even close. The real genius, the absolute game changer, wasn't just in sorting them. It was in the arrangement. And that led to one of the most famous charts in all of science.
And this thing, it is so much more than just a list. It's an incredible map where an element's location, its address on the grid, tells you its entire story. It tells you its family, predicts how it's going to act, and even who its friends are. It's pure genius.
And the story of how we got it is a perfect example of science in action. First, you have Dmitry Mendeleev, who saw the patterns so clearly that he had the confidence to leave empty spaces on his chart for elements that hadn't even been discovered yet. Then, years later, Harry Moseley came along and tweaked the system, giving us the super accurate version we use today.
So, how do you read this thing? Well, it's basically a grid. The rows going across are called periods. The columns going down are called groups. And an element's address, its period and its group, is the secret code to understanding everything about it.
Okay, enough theory. Let's make this real. We're going to go meet a couple of the chemical families that live on this map. We'll pick two from totally opposite sides of the neighborhood to really see this pattern in action.
All right, first up, let's head all the way to the left, to Group 1. Meet the alkali metals. If these guys were people, they'd be the super energetic, can't-sit-still extroverts at the party. They are so reactive, they literally have to be stored in oil just to stop them from freaking out and reacting with the air around them.
Now let's take a leap all the way across the table to Group 17. These are the halogens. Now, they are also extremely reactive, but with a totally different vibe. And you actually know these guys pretty well. Chlorine is what keeps pools clean, and their name literally means salt former because they love pairing up with metals. And this brings us to the big mystery, right? We can see the pattern. We know that elements in the same column act like a family. But why? What's the hidden rule that makes them behave this way? Well, to find out, we have to go deep inside the atom itself. So let's zoom way in. Every atom has a core, the nucleus, and then it has electrons buzzing around it in different layers, kind of like planets orbiting a star. We call those layers electron shells. The number of protons in the center is what defines the element, and that also tells you how many electrons are buzzing around. But here's the thing, it's not a free-for-all. There are really strict rules for where those electrons can go. The best way to think about it is like assigned seats at a concert. The seats closest to the stage, the nucleus, they fill up first. That first row only has room for 2 electrons. The second row has room for 8, and so on.
And right here, this is it. This is the secret, the key that unlocks the whole thing. It turns out, when it comes to an element's personality, it's not the total number of electrons that matters. It's only the ones way out on the edge, in the very last shell. We call those the valence electrons. So get ready for the big aha moment. Let's go back to our super reactive friends from Group 1, the alkali metals. We're going to put lithium and sodium under the microscope and check out their electron situations. Okay, check out lithium. It has 3 electrons. 2 of them fill up that first shell, that first row of seats. And that leaves just 1, all by itself, in the second shell. Now look at sodium. It has 11 electrons. The first shell fills with 2, the second fills with 8, and what's left over? 1 lonely electron in the third shell.
Are you seeing it yet? That's the magic number, 1. Even though they have different numbers of shells, they both have exactly one valence electron. That single electron hanging out in their outermost shell is the secret handshake of their family. It's the source of their shared, super reactive personality.
And suddenly, it all just clicks into place. The periodic table isn't just a clever chart someone made. It is a visual representation of a deep, fundamental, repeating law that's built into the very structure of atoms. And this is why it all works. The periodicity, that repeating pattern Mendeleev saw, it's the repeating pattern of those outermost electrons. As you move down a column, or a group, the number of valence electrons stays the same. That's what makes them a family. That's the whole game.
So think about that journey. We went from a chaotic jumble of cosmic ingredients to this elegant, powerful, and predictive map. And it's all because of the simple, repeating behavior of the tiniest particles in the atom. You know, the true genius of the periodic table was its power to predict things, to reveal a hidden order to the universe. And it just makes you wonder, doesn't it? What other profound, hidden patterns are all around us, just waiting for someone to finally draw the right map? Something to think about. Thanks for tuning in.